All right, guys. So we're moving on a little bit to some applications of Le Chatelier's principle. And again, Le Chatelier's principle was an equilibrium system. If you stress it, that equilibrium system will shift or react to counteract the stress that you place on it. And again, equilibrium was equal rates of change in a reaction, reversible reactions, equal rates of change that are actually quite, if you want to think about it, it's kind of boring. Equilibrium is just this state of, static where you have, two reactions taking place, canceling each other out, or, constantly producing reactants and products. But it doesn't seem to really do much until we start to kind of use it to our advantage and start to change the equilibrium. So let's take a look at a couple of examples. All right, so systems at equilibrium tend to want to stay that way. That's true. All right, and when we disturb them or stress them at equilibrium, and the question becomes here is, can we use this to our advantage? What happens as a result based on this shifting? Okay, and when we stress systems out. So we're going to, give you a quick example here. All right, so let's try it out. So ammonia, which is NH3, is an important compound which is used as a raw material in cleaning agents, fertilizers, and many other products. So ammonia is a pretty important compound. However, the natural production of ammonia is very inefficient, which means when you make it, you really don't make a lot of it in reaction because it goes to equilibrium. All right, it produces very little ammonia at equilibrium. Now, let's think about this. If you're selling ammonia and you want to make ammonia, the fact that you create very little of it is not very advantageous to us. Okay, so if you were to look at the reaction of ammonia, you would take some nitrogen, some hydrogen. They would react together by colliding, right? We have collisions, and you would create some ammonia molecules. But those ammonia molecules actually break back up in reverse and reform the nitrogen and the hydrogen. So I gave you a little picture of a reaction vessel here, and I want you to look at this reaction vessel for a minute. And it's not really crucial how much you have in here right now. Just look at the relative amounts of ammonia versus nitrogen and hydrogen. And you can see there's a lot more reactants here than there are products, right? So these are the guys you're actually selling, right? You're selling ammonia. And if you're selling ammonia, you want to make ammonia, it's not good in this case because you're just not making a lot of it. Most of it's breaking back up and reforming the ingredients. All right, that wouldn't be good if you owned a bakery and all your bakery products kept breaking back up into the raw materials. How would you sell anything? So we want to be able to, change this around. Is there some way that I can push the reaction to create more ammonia and less reactants? All right, and that's what we can use Le Chatelier's principle for. So the question becomes, how can we disturb the equilibrium to produce more NH3? Okay, so we want to find a way that we can push the reaction to the right. We want to make the right-hand reaction, okay, faster. Okay, so that would be the right and that would be the left. Okay, so what we can do is we can use our stresses. We can use our concentration, our temperature, our pressure to increase the forward reaction. All right, and this is, again, one way that we can see Le Chatelier's principle. Again, one of the many ways. All right, so let's give it a shot and see how we can do. All right, so I'm going to look at this in a different way. I'm going to look at my reaction vessel, okay, and I'm going to see that I have these are going to be called shift arrows. So in our discussion here, shift arrows are shifting to the right here or shifting to the left, okay. And when I mean shift, okay, shift is an important word in this case. When I say shift to the right or shift to the left, that simply means shift means to go faster. That means that reaction goes faster temporarily. It speeds up. That reaction speeds up or speeds up. Okay? So if I shift right, that means I speed up to the right. If I shift left, I would speed up to the left. Okay, so that's really important vocabulary for this. So let's look at concentration. How can I manipulate this so that this would go faster? Okay, and that's the important thing today. So concentration. Let's use so in these brackets. This bracket's always going to mean molarity. So let's just say that I increase my amount of N2. Okay, so what I mean by that is I open up a little hole in here and I put in some extra N2. Okay, so I'm going to add N2. Now, if I add N2, there's going to be more collisions between the N2 and the H2 that's already there, right? I'm adding more molecules of H2. Of N2. Now, if I add more molecules of N2, again, more will be available to collide. Just like if you add more particles to a solution, there's more collisions when we talked about collision theory. So more collisions will take place between N2 and H2. So what that's going to do is that's going to cause the reaction to shift to the right, which simply means the reaction is going to speed up to the right, okay, and that forward reaction rate is going to increase. So basically, this red arrow here is going to be a faster reaction temporarily because I added more N2. Now, what the system wants to do is take that N2 and create more NH3 with it because that would get rid of the N2 that I added. Okay, so basically, I'm going to shift to the right. Okay, now shifting to the right means I'm going to speed up to the right. Okay, and now I'm going to increase my concentration of NH3. Okay, now because I'm increasing my concentration of NH3 and I did not add more H2, I only added more NH2. I'm sorry, I only added more N2. I didn't add more H2. So if I'm going to make more NH3, my H2 has to decrease, okay, as it is used up faster to make more NH3, okay? So in summary, this is what we're doing, and this is where I want you to see how we're going to do this. I'm adding N2. I'm going to shift to the right because adding something produces more collisions with this reactant on the same side. I'm going to shift to the right, okay? It's going to cause my NH3 to go up and my H2 to go down. And what I want to do is take a look at my shift arrow. Now again, this shift arrow is the arrow you want to find when you find the shift, okay? When you shift to the right, the arrow, whatever that arrow is pointing to, will cause something to go up. Whatever that arrow points away from will cause that thing to go down. Okay, so that's how we're going to work this. And again, shifting to the right or shifting to the left has the same effect. Okay, now let's just say we were to remove N2. If I was to remove N2, okay, so let's say I go into this container and I take out some N2 molecules. If I take some N2 molecules and I start removing some of these guys, okay, I have less to react with the H2 and more room for the NH3 to decompose and go back the other way. Not only that, because I'm taking out my N2, the reaction wants to now recreate the N2 that I took out. So I'm going to shift to the left to recreate N2. So I'm going to remove N2. Okay, there's going to be more collisions of the NH3 molecule. The reverse reaction rate is going to increase. I'm going to shift to the left, and now H2 is going to go up and NH3 is going to go down. So I'm going to take a look at my result of my arrow. So if I remove something, okay, I am now going to shift to the left. Whatever that arrow points to will go up. Whatever that arrow that points to will go down. Okay? Now again, what the system is simply doing is just adjusting to you adding and removing things. Okay? And that's going to be important to know. All right? So a couple of things you want to think about in this is a couple of hints you want to have here. Okay? If you add something, you always add shift away. So think add away, okay? And whenever you remove, you're going to shift towards. Okay, so shift towards. So add away, shift towards. So again, if I add, I'm shifting away from it. If I remove, I'm shifting towards the thing I remove. Add, shifting away, removed, shifting towards. Whatever the shift arrow points to goes up. Whatever the shift arrow points away from goes down. Whatever the shift arrow points to goes up. Whatever the shift arrow to points away from goes down. Okay, this rule works every single time. All right, so that's for concentration. Concentration is your first stress. Okay, now so that's pretty good. So we can manipulate this. So if I add N2 or add H2, I'm going to shift to the right and produce more NH3. Okay, all right. So next thing, what if I want to take a look at pressure? Okay, so pressure is interesting, and pressure is going to be for gases only. This is really important. All right, so if I check my reaction, I'll see I have a gas here, and a gas here. Again, I have my shift arrows, okay? And again, pressure affects gases only. Now, I want you to take a look, okay? When you increase the pressure on this, you're also going to decrease the volume. So I want you to imagine taking this container now and compressing this into a smaller space. So I take this big box here and I increase the pressure, okay, by putting it into a smaller place. Okay, I increase the P, or I decrease the volume. Again, increasing the pressure and decreasing the volume is the same thing. That came from Boyle's law. Don't forget your gas laws. All right. What we're going to do is you got to think about this. If we do this, what does the system do? The system says, okay, you're going to put pressure on me. I'm going to get into smaller molecules or smaller space because I have to adjust to the fact that you're putting pressure on. So I'm going to react to produce the smallest amount of total moles of gas. Okay? Now, if you take a look at this reaction, you'll see there's 1 mole of N2 and 3 moles of H2. So if you put that together, you get 4 moles of gas on the left. And when you react to form ammonia, you actually combine these to create 2NH3. So if you take a look even here, you'll see if there's 1 N2 and 3 H2, that actually gets together and forms 2 NH3, which takes up less space. All right. So that would cause me to shift to the right. So if I'm going to shift from 4 moles to 2 moles, that's my shift arrow. And again, whatever that shift arrow points to goes up, whatever the shift arrow points away from goes down. All right. So that's going to be an important part of this reaction. Okay. So let's do it. All right. So what's going to happen is I'm going to shift to the right. If I shift to the right, my NH3 will go up. My H2 and N2 goes down. Okay. The reverse occurs when you decrease the pressure. That's important to know. If your moles are equal and you have moles are equal on each side, there is no shift at all because you just maintain the equilibrium. Okay, so here's your summary. The summary is you add pressure, you have 4 moles of gas on that side, you have 2 moles of gas on this side, you shift towards the lower moles, whatever that shift arrow points up, goes up, whatever the shift arrow points away from goes down. Really important. So your N2 and your H2 would decrease, and your NH3 will go up. So for me, if I'm selling ammonia, it's advantageous for me to increase my pressure. Okay, really important. And don't forget the reverse occurs as well if you decrease the pressure, if you go to a larger volume. All right, again, find that shift arrow. All right, temperature. Temperature reacts very similar to concentration. Again, if you take a look up here, you'll see the temperature or the heat is actually on the right side of the reaction. And if the heat is on the right side of the reaction, that reaction is preferentially exothermic going forward. Okay, you can actually squeeze it in the air. It would be exo going forward. Okay, and endo going in reverse, really important. Okay, so what's the rule on temperature? The addition of heat, if you raise the temperature, speeds up the endothermic reaction preferentially. You're favoring that endothermic reaction. Endothermic reactions absorb heat. So if you add heat, you're just making it go faster. Good example is an ice cube. If you have an ice cube, okay, and you add heat to it, and you continue to add heat as a stress from the outside, that ice cube will melt faster. Okay, so the endothermic in this case, the reaction, is the reverse reaction. So you will speed up the reverse reaction. So that would be the shift to the left. Okay, so you add heat, or by increasing the temperature, you're going to shift left. Okay, your H2 and your N2 will, of course, go up because you're going to be pointing to them. You'll go faster in that direction, and your NH3 will decrease. Okay, so the reverse reaction happens when you're decreasing T. This can be tricky. Remember, all collisions are affected by temperature changes, so you got to keep an eye on this one. All right, so here's a good example of increasing if you're adding heat, you're going to shift, again, adding shift away. If you shift left, there's your arrow, your shift arrow. Whatever that shift arrow points to will go up. Whatever that shift arrow points away from goes down. All right, so again, adding a lot of heat to this in the beginning may not be a good issue because, again, we were looking to raise the amount of NH3 we're making. So good so far. Okay. I want to go back. One more thing you want to add to this is the fact that a catalyst, again, you can add a catalyst. Well, actually, we can do it right here. This is probably a better idea to see it. Okay, so what's your summary? Your summary is of Le Chatelier's principle. And again, we could do some examples of this. If a stress is applied to a system at equilibrium, the system will shift to counteract the stress that you add. Okay, so it's important to know. You're going to add away, remove towards. All right, so a couple of ideas. Your stress is concentration. Okay? So the concentration ones, I'm going to circle this here. If you take a look at concentration, if your stress is concentration, again, these two guys will be concentration. We're going to add away, we're going to remove towards. If you add something, that means the concentration needs to be used up. If you add it, it wants to use up. If you decrease the concentration of something, the system wants to make more. Okay, so why? What does the system want to do? So why are you doing this? You're thinking of the collision theory. Okay, if you increase the pressure, you're going to shift towards fewer moles. If you decrease it towards more moles, why are you doing this? Because an increase in pressure looks at a volume decrease. A decrease in the pressure looks at a volume increase. Again, the system wants to take away what you're doing. All right. Temperature. If you increase the temperature, you're going to go away from the heat. Okay. All right, and there's a mistake here. This should be endothermic. That's endothermic is favored. Endothermic, not exothermic. Okay, so if you increase the temperature, the endothermic reaction is favored. Why? Well, you added temperature. The system wants to use up that energy, so it goes endothermic. If you decrease the temperature, you're going to go towards the temperature, which is it wants to make more. So it wants to produce more heat if you take it away. All right, so that's important to know. And again, really important to remember as a catalyst, there is no shift whatsoever, okay? Because the rates of both the forward and reactions are increased by the same amount. So a catalyst just makes you go faster in both directions. And if you go faster in both directions, then it doesn't do anything. It's like the speeding limit. If you change the speed limit on both sides of a road to the same speed and you increase that speed limit, the cars on both sides of the road go just faster, but they don't change in relationship to each other. So you're going to think Boyle's law for the gases, and you're going to treat heat as if it was another reactant or product. All right, so really that's Le Chatelier's principle really quickly. Let's do a couple of quick examples so we can see how you'd actually do this on checking things. All right, and that's important to know. Okay, find your shift arrow. That's what I would say. That's probably your best set of advice is to find that shift arrow first. Anything that shift arrow points to goes up. Anything that shift arrow goes away from goes down. All right, so let's try an example, quick example here. We'll go through this very quickly. Again, if you have to, check it and slow down the video or watch it again, that's fine. Okay, so let's just say we have this this reaction, okay, in our beaker, and it is an interesting one. You have N2O4, which is a colorless gas, and if you add heat to that and you heat it up, it actually becomes dark brown and it separates into these two gases, NO2, 2 times NO2. Okay, and if you take away heat, it goes and becomes colorless. If you add heat, it goes dark. So back and forth, this can change its equilibrium. So let's just say we add N2O4. So I'm going to add so if I add N2O4, I'm going to shift to the right. I'm going to go in that direction. I would actually lower my, again, I can do this on the screen. I'll just have to continue to erase it each time for you. But all right, so if I add N2O4, I would shift to the right, and whatever I shift to points and goes up, and that means my heat would go down. So my heat decreases, my NO2 goes up if I shift to the right. Okay, so that's a good one. Let's check. Let's do the next one. Okay, what if I add NO2? If I add NO2, I'm going to shift away from NO2. My heat would rise. My N2O4 would rise. Okay, so I shift to the left. My heat goes up. My N2O4 goes up. Okay, next one. Okay, if I remove heat and lower the T, well, if I remove something, I'm going to shift towards the heat. Okay, if I shift towards that side, whatever I'm pointing to will rise. Whatever I'm pointing away from will fall. Okay, so I shift to the left, my NO2 goes down, my N2O4 goes up. So you're following the same pattern. Whatever that shift arrow points to goes up, whatever the shift arrow points away from goes down. Again, it's crucial to find the shift arrow. Last but not least, what if I increase my pressure? If I increase my pressure or lower my volume, I'm going to also always push towards the lower number of moles. I have 1 mole on this side. I have 2 moles on that side. So if I increase the pressure, I'm going to shift towards the lower number of moles. This is going to go up because I'm pointing to it. That's going to go up because I'm pointing to it. That's going to point away from I'm going down. So I'm going to shift to the left. My heat will be increases. I will release heat. Okay, I will increase my amount of N2O4, and I will decrease the amount of my dark brown gas, NO2. So that's exactly how you would do this. I think it's very important to be drawing these arrows up here, okay, for each example. It makes things a heck of a lot easier to figure it out. Okay, so last night, that's example number 1. Let's try example number 2. All right, and then we'll be done with this. Okay, again, we'll go through pretty quickly. Let's just say I have my example of SO2 plus O2 makes SO3 plus heat. I got this reaction at equilibrium. I have all gases. Let's go through it. Why not? So if I increase SO2, so if I add SO2, okay, I'm going to shift, you guessed it, to the right. SO3 goes up, heat goes up, oxygen goes down. So I'm going to shift to the right. Okay. Again, there's more collisions between these two guys. More collisions means I'm going to create SO3 faster. Okay, so my O2 will decrease. My SO3 will go up. My heat will go up. Okay. So I'm going to let you see that really quickly on that. Okay. So I'll get rid of that, get rid of that. We'll do another one. I'll have to keep doing this kind of thing. All right, so what if I decrease? So if I remove this, I'm going to shift towards that, right? So I'm going to shift left, okay? If I shift towards that left side, my SO2 will go up, my SO3 will go down, my heat will go down, okay? Let's see if I have a little... There's no really way. Okay. All right, so number 3. So number 3, if I have... if I increase my SO3, if I add SO3, if I add SO3, okay, I'm going to shift away from my SO3. My O2 will go up, my SO2 go up, and my heat will go down. Again, whatever I'm pointing to goes up. So if I shift to the left, okay, I will have my O2 go up, my SO2 go up, my heat go down. Okay, and again, I have to keep erasing it here so I can rewrite my diagram. All right. So if I add my heat, if I add heat, I'm going to shift away from the heat. My O2 goes up, my SO2 goes up, my O3 goes down. So I'm going to shift left, my O2 goes up, my SO3 goes down, my O2 goes up. Okay, and so on. All right, so I'm going to fill in the last answers for you, and you should be okay. If I remove heat, I will shift to the right. Okay, if I shift to the right, my O2 goes down, my SO3 goes up, my SO2 goes down. If I increase my pressure, let's take a look. Are we all in gases? Yes, we are. We have 3 moles here. We have 2 moles here. I'm going to shift in the direction of the lower amount of moles. We're shifting to the right. So if I shift to the right, my O2 goes down, my SO3 goes up, my O2 goes down. All right, so you get the idea. I hope you're not too stressed. And that is Le Chatelier's principle, shifting to the left, shifting to the right. Please make sure you practice. Please make sure you do the problems in the packets and make sure that you're staying on top of this. And then we will see you next. Have a great day.